Okay, good afternoon, everybody. I hope everyone's having a wonderful day. So today we're going to be talking more about regular expressions. Now, before I get to that, I just have a couple of quick reminders. So just remember that next week, assignment 1 is due. It is due essentially a week from now, roughly. You have until 11:59 p.m. That's the deadline. However, I will keep the submission open till about, I'm trying to remember off the top of my head, I think it's like 7:30 or 8:30. I can confirm that Regina time. If say you really just need that extra time, or there's a technical issue, if you need more time and that bullet right for the midnight is not good enough, and you need like a couple more hours or something like that, whether it be to work on it more or anything like that, it's mostly there for technical issues. But if you really need that time, I think it's just kind of pragmatic. It makes things easier for all of us because one, I'm not going to look at your assignment while I'm sleeping, so I think we're doing all right with that. Is that clear, everybody? So just remember, you have to submit your assignment as a single PDF file. Okay. So other than that, make sure you complete this onboarding quiz on your courses page. You have to do it by the end of September 30th. We need that just for when we later on get in the course for the final exam, because towards the end of this, well, for the final exam, we're using Proctor Track, one of these necessary evils of sorts for this course. And it requires this onboarding process. So make sure you please complete it for this class. You have to do this for each one of your classes. Just need to be clear about that. So are there any things before we get started? Or are we all good to go? Give me thumbs up if we're all good to go. Okay, I think we're good. So let's get started. So I wanted to just give us just a refresher from last day, just so that we're comfortable with these so-called regular expressions. So remember, we can use regular expressions to describe languages. So I talked about these regular operators previously in the course. I've shown you how you can define them using regular expressions last time. So I thought I would kind of go through some examples here, just to make sure that we remember that regular expressions still represent languages. So I thought I would kind of walk us through just a quick number of examples. We'll do one more example, then I'm going to get to something much bigger. So that's the plan for today. So I thought I would just start off by just walking you through this process, just to make sure, remember, we still have the intuition when we read a regular expression, what it means as a language. So if I give you, I want to know the language of the following expression. Can somebody tell me what that language is? So what's this language? What is the language of this expression? So look, it's just a symbol 1, a symbol 0. They're expressions, or I concatenate them. So what does that mean? So what should I write right here? Yeah, 0. Well, is it 0 or 1, or is it just like the string 1, 0, or is it this? Yes. Yeah, it's just the string 1, 0, right? Because this is, so if we want to break this down a little further, remember, this is just the language of the expression 1 concatenated with the language of the expression 0, right? Because it's concatenation happening right here. But what's this? This is 1, and I'm concatenating it with the set containing the symbol 0. But that's just, whoops, 1, 0. Is that clear, everybody? Just remember, when you read off an expression, if you ever are unsure what it means, you can always appeal to the definitions of what these regular operators mean. So are we good with this example? I just want to be clear with everybody, because I'm going to kind of go boom, 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 boom with everything else. Okay. So, can somebody tell me what is this language, though? Can somebody tell me what this language is? Like, what's the language of this expression? So notice the plus sign means union. So remember that. Yeah, 0, 1, and then there's another string with just the symbol 1, right? Because remember, the concatenation of two of these is just, it's just 0, 1, because this is what this means. It means this is the expression for the symbol 0. This is the expression for the symbol 1. I've concatenated them, so I get the expression that represents the set containing the string 0, 1. Here is just the expression for 1, so it's just 1. And since this is union, I'm just going to take those two sets, dump them all together into one set. Okay, so this one, notice, remember, when it comes to the order, regular operators are applied. You'll remember that this is just really, if you think about it, this is like if I have 0, I concatenate it with the union of these two. So that would just be 0 and 1 like this, right? So that would mean that this should be what? Can somebody tell me what that is? Yeah, I think we're doing good on that. So we've got, yeah, because we should get, yeah, 0, 0, 0, 1. Yeah, very good, very good. Okay, now 1 star is nice and easy. Okay, you just apply the star operator on the symbol in question here. So you just start off with epsilon. I take none of them. I got 1, 1, 1, 1, 1, 1, and so on. Here, this is where it gets a little trickier, and you have to think about this a little bit more. So on the next assignment, I'll be giving you some of these, and I might ask you to like write them out in plain language for me, like just describe them to me. So this one I'm going to help you with, but we're going to kind of walk through it. Okay. So remember, this is a star operator here. The first question I have is, does this thing accept the empty string? The answer, of course, is, let's see. So if I have the star operator on all of this, that means I could take none of this entire expression, which means that that's epsilon. And I also could take, I could take this epsilon right here when I do the concatenation, so there's better accept epsilon, right? Okay, does it accept the string 1? Just with the symbol 1, that's it. Let's see. You got 1 here. And you can take this one or this one. I like to think of the union like an or. So I could take the 1, I could take it once, I could take the epsilon here and I could get 1. I could take none of these. I could take the 0 and I get a 0. Okay, how about 0, 1? 0, 1 is right here. So I could take this one once, I could take the epsilon here. And can I take 1, 0? Well, let's see. We got 1 here. And then I could take the 0 here. I could get 1, 0. Now I have an interesting question for you. Can I take 1, 1? Can somebody tell me yes or no? Well, let's think about it. Let's think about it. I have the star operator on this, so I can go 1, 1. So like, remember, I could take the 1 as many times as I like. So I could go 1, then I could take an epsilon right here because I concatenate it with epsilon. So we can indeed do 1, 1. But here's the interesting question. Can you do 0, 0? So for the person that said yes, how do you do it? So don't be shy. Okay, so let's see. So look at this. So I have something with a 1 and then a 0, 1 here. So I can take as many 1s or 0, 1s as I like. Then I concatenate that either with a 0 or nothing. So if I try to get a 0, 0, the question is, where does that appear? Does it appear at all here? And I heard somebody say no, and that would be the correct answer in this case. Is that, notice that there is no way to produce 0, 0 from this. So notice that I can't, like, it'll be like 0, 1, 0. I can get 0, 1, 0, 1, 0. I can get 1, 0, 1, 1, 0. like I can get a lot of different combinations, but notice I can't get 0, 0 with any combination of other strings. Does everybody see that? So notice that I could build any binary string except for only one possibility that could be inside of one of my strings as a substring. So this is just simply, so you can see that this is the set of binary strings. The binary strings that do not contain two consecutive, that means one after the other, consecutive zeros. Does everybody see that? So I can produce as many ones as I like. I can get 0 ones. I can get a bunch of 0 ones. I can go 0, 1, 0, 1, 0, 1. But notice that I can create any combination of a single 0 afterwards, but it has to be followed preceding by a 1, or it just has to be a 0 on its own. But I can create every other combination using this, right? So if, say, I wanted to describe this, this is one way I can describe this. If you're not convinced by this, I recommend taking this apart like I did in these previous examples and try it out. Are we okay with this example here? I just want to make sure that we're on the same page with this. Is that I can take, yes, please. Okay. Yeah, so, okay, so the epsilon here, the order of these, the answer is no, it doesn't matter. One thing that's worth noting is that the union, so this plus, is in fact associative. So the order in which you list it, so if I had like x plus y, it doesn't matter if I write... Like this coming before right here. That's actually a really good question. I haven't thought about that when I was... Yeah, so this one, okay, so let's see. So we can go 0. Okay, so this one, I think you can get it to have a 0, 0 in it, but it won't have 0, 0 itself in it, I think. So, for example, if I move this over here, I can have it so that I can accept straight. So I don't see a way you can get 0, 0, but you can get 0, 0, 1 by taking the 0, then you can take this one right here and have 0, 1 afterwards. So the order here does matter. Like concatenation, it definitely does matter, but in this case, it doesn't really get us that over there. It gives us something else. But that's a really good question. But yeah, no, you can definitely get it so that so here I can get 0 like this. I can't get the 0, 0 like this on that if I flip it over here. However, I can get this. And I can alternate I could get as many ones as I like. I can have 0, 1, 0, 0, 0, 1 after this. But it doesn't have the, like, I end up having it so I don't accept on this, but I can still get the 2 zeros. But the question is, where it happens, yeah, you probably won't be able to get a 0, 0 to appear somewhere after this, probably. I'll let you think about it. I think that's actually a really great question. I do appreciate that one. Those are the types of questions I really want you to start thinking about when you look at things like this. Is like, okay, well, what happens when I flip it like this? Does that happen? Does this change it up a little bit? That's actually really why I really wanted to show you some of these examples, is so that we can get kind of a flavor for what we can express with a regular expression. Pun intended. Are we all good with this? Because I want to proceed to one more example, and then we'll do something much more, I would call it spicier or interesting. Okay, I think we're good. So let me proceed to do one more example. So I wanted to revisit the example I did with the epsilon NFA. Remember I had this example where I was reading decimals? So I'm just going to do this reading decimals example. Now, I'm just going to remind you what this example what we did. We designed an epsilon NFA that had the following property, that it optionally plus minus, so I can optionally have a plus or minus out front. Then I'd had 0 or more digits, a dot, then a string of digits. So this had to be at least one symbol on this one side. And then it was the other side I had it where it's a string of digits. So there's kind of like two possibilities. Either this happens or this happens. A string of digits. And there's at least one symbol when I say that. A dot. Then a 0 or more digits. So I'm just rephrasing what we did when we did the epsilon NFA. Remember, I had that one where I had the loop with like the transitions like with 0 all the way up to 9. So I'm going to show you how I could do this with a regular expression. So I'm going to show you how I could take some regular expressions and build them up. Because you remember in the basis definition of the regular expression, I told you that I'm allowed to have a symbol. Like I mean this like a capital letter that represents an expression. Well, I'm going to show you how I can use that just to make it a little easier for us to see. So if I wanted to design this, I could take this into 3 parts and dissect it. So if I have something a little bit more complicated I'm working on, I can take, say, simpler expressions and then apply regular operators to them to get the more complicated one. So could somebody tell me, assuming that you had symbols plus, minus, could somebody tell me a regular expression? I'm going to call it E. Could somebody tell me a regular expression I could use that should give me the language that consists of plus, minus, or epsilon? So plus, and then there's like, so now it's worth knowing this is a union. Yeah, you got it so far. Yeah, you're gonna have epsilon, and then you're gonna have a minus. Is that right? Like this. I'm gonna underline them to make this less confusing. Okay. This is one of those things, those strange circumstances when we have symbols that mean other things. So this is me referring to the regular expression that represents the symbol plus, this is union here, and that's union as well. So notice that here I can use this, and this will give me a plus, a minus, or epsilon. So we're going to use this epsilon to give us an option. And do you remember in our epsilon NFA, that's exactly how we used epsilon? Is that neat? So now I'm going to go to the second case. So I'm going to kind of plow through this a little bit. So the first thing you should remember from last time is if I want to get any one of 0, 1, all the way up to 9, I can take and I can perform unions among all of them, and I can apply a star if I want as many of them as I like. So we did that last time, right? So if I want to have, say, 0, 1, all the way up to 9 like this, this will give me one symbol from these. I'm going to apply the star. So this will give me 0 or more digits of 0 through 9. Does everybody see that so far? Are we good? Give me a thumbs up if we're good. Excellent, excellent. So now naturally we're going to need a dot. And now this is where this gets fun again, because remember I told you last day that you can use also a dot to represent concatenation. So I'm referring to the symbol that's a dot, a decimal point. And then I tell you that I need to have a string of digits, but I need at least one on this case. So does anybody have any ideas of how I can do that? Any ideas of how I could get at least one symbol to be there? I'll get us started. How about if you wanted to have exactly one symbol? So let me write just that. So if I want to have one symbol, I could just write this, right? Now, does anybody have any ideas how I can modify? I could take this and make it so that I could accept more digits. So I see. Let's see. I'm thinking if that's from earlier. I think it might be from earlier. So I'm going to need. I would recommend we're going to use probably concatenation here. But what would you concatenate it with? Yeah. Yeah, exactly. Very good. So I'm going to just take that, and then I can put the star on it. Bang. Oh. Okay, gotcha. Yeah, no, so notice, so let me now read this off to you, and you can see how I'm describing this case right here, the second one. So notice I take 0 or more digits. So the star allows me to take none. Then I have a dot. Then I have at least one string, at least one symbol along with my string of digits here. So I got my 0 through 9. This guarantees that there is exactly one. Then I have this here to guarantee me that it's either exactly one or more. Does everybody see the little trick I did there? So this forces me to have one or more. So the natural thing is once I have that, I could just simply reorder what I did here for the second case. So I have a string of digits, so I need at least one. So naturally, I'm going to have to use the same kind of trick I just did a moment ago. So I have 0 through 9. I'm going to put a star here, and then I'm going to concatenate it, just like I did before. So then so now I have, this will allow me to get me at least one symbol for a digit. And now I need a dot. So I'll just concatenate it with the symbol that represents the decimal place. And then I need 0 or more digits. What should I stick right here? Yes, all the digits with plus, and then star. Perfect. See, you guys are pros. I like this. So now, can somebody tell me, using these three expressions, E, F, and G, how do I design my regular expression to do all of this? So remember, it takes an optionally a plus and minus, then it could do one of these two possibilities. So first, yeah, so we got E. Now let's think about it. We want to have E, then one of these two cases happen. So E, here's what I recommend we try doing. We try concatenating something. Yes, F plus G. Isn't that nice? So now notice, look, bam. So notice that I can take the optional symbol N, and then I can satisfy one of these two possibilities. One is F, the other one's G. Is that neat? So do you see how I can take expressions and I can use them to build more complicated expressions? So that's I wanted to illustrate that to you because that was one thing that I didn't really highlight a whole lot from when we talked about regular expressions last day, is that in my regular expression I can use other expressions by representing them like this. But yeah, see, I could design a regular expression that describes the same language as our epsilon NFA did that other day. Is that nice? Are we all good with this? Give me a thumbs up. I need to know that you're all good with this. Just don't be shy. Okay, I'm seeing some thumbs up. I see a thumbs up. Awesome. Okay, good. Excellent. So what I want to do is I want to now talk about Oh, let's see. I have a great question. I think I see a question in the chat. Let me grab my mouse here. Let's see here. So, don't we have a Kleene plus operator? Yes, that does actually exist. I don't think I can't remember if I talked about that earlier. There exists another operator called Kleene plus or Kleene plus, sorry. So sometimes it's denoted, instead of a star like this, you have plus like this. So instead of using star, you'd use a plus, but it's like this. I didn't define this one, I think, for you guys. But that is an alternative that does actually exist. I think the Sipser book actually does give this one. But I don't think I've defined that one. I just talked about star, just star like this. But that does exist. I am very well aware of that one, and I think it's glad that somebody pointed it out to me in the class here, because this does actually exist as notation for if you want to guarantee that there is at least one. So it's for one or more occurrences. So that is something that does exist out there. I don't think I defined that one for you, but if you want to use it, go right ahead. But yeah, no, thanks for pointing that out. Actually, I do appreciate that. Let me see here. So let me move on to what we're going to basically talk about the next couple of lectures. I consider this one of these like I told you when I talked about the NFAs and DFAs and we did the equivalence between the two, I told you that was essentially this really like important idea. This is going to be another one of those. So we're going to talk about Kleine's theorem. Like I said, we're going to talk about Kleine's theorem for like 2 lectures at least. So Kleine's theorem is going to be effectively the characterization of everything we've talked about up until this point in terms of finite automata and also these regular expressions. And the theorem goes like, here's a theorem that's named after Stephen Cole Kleene, who developed a lot of the early theory around regular expressions. So this is often attributed to him. A language L is regular if and only if there is a regular expression that describes L. That is, the languages described by regular expressions, and finite automata, or finite state automata. I'll say finite automata if I feel like being a little shorter with you today. When I say that, I'm talking about, of course, your DFA, your NFA, and your epsilon NFA are regular. Or equivalent, whatever way you'd like to write it. I'll just write are regular. But bam, that's a pretty powerful theorem if you think about it. So so this theorem is going to characterize every one of the finite automatons that we've seen in this course, plus the regular expressions. So the answer whether that the regular expressions have more power to express more languages or not is actually that they express the exact same set of languages. So I'm going to kind of give us an overall sketch or plan of what we're going to do to prove this theorem, because we already actually have bits and pieces of it. So to prove this claim, we use the following framework. The following framework. Oh, it says framework. So here's how I'm going to do it. So I swear this is one of these things that will be helpful to remember is this picture. Is that if you wanted, so if I'm going to imagine I'm going to have 3 circles here. One of them is going to represent my regular expressions. One's going to represent the epsilon NFA, and one's going to represent the DFA. So the way I'm going to prove the equivalency of all of them, because remember, it's not relevant for our proof really so much because we proved it previously, is that the NFA and the DFA, these are equivalent, right? We proved this before. So what we're going to do is I'm going to, so 2 parts of this proof are this part, where I have to prove to you that given a DFA, that there's a regular expression that accepts the same language, or describes the same language, if we have to be a bit more precise. The other thing that I'm going to try proving to you, this is the one I'm going to focus on, is I'm going to show you how you can take a regular expression and turn it into an epsilon NFA that accepts the same language, or recognizes or describes the same language. In particular, describes it, because regular expressions, we describe things. But we already actually have one piece here already. We have this one. So remember that this is our modified subset construction that we use right here. So we could turn any epsilon NFA to a DFA using the modified subset construction I gave you the other lecture. So we only have to prove 2 parts to this. So I can take a DFA, turn it into a regular expression. Then I want to show you how you can take a regular expression, turn it into an epsilon NFA. So I want to convert between them. But you would agree with me that if I have an epsilon NFA, I can turn it into a DFA, then turn that into an NFA. Right? So this should give you a nice roadmap for which you can do this. It's worth noting that there do exist more arrows, but this one, everything I have in this triangle is what's going to be relevant for proving this theorem. Are we all okay with the sketch here? So this is going to be the overall idea. So I'm going to prove one direction for you today. So I'm going to prove this part to go from here to there. Okay, so let's do that. I wanted to do this one first because I personally really like this part of the proof. So I'm a little biased in that sense. That I decided I wanted to pick this part first. I just think it's really neat because you'll see when I describe the NFAs to you, the epsilon NFAs, and I showed you the regular expression, did you see that there's sort of a way I was describing the regular expression to you that it looked kind of like I was like mushing down the epsilon NFA into like a line? It was sort of like that. And I want to show you how you can take a regular expression and basically bump it out like this, like a pump-up tent or something. Like just pop-out tent. I'm going to show you how you can take something like that and build an epsilon NFA. So we're going to do this using induction. So here's a theorem. Here's a theorem. If L equals the language of R for a regular expression R, then there is an epsilon NFA E where the language L equals the language of E. So what I'm going to do is I'm going to try to build for you an epsilon NFA, but I'm going to use induction on the number of regular operators. And the way it's going to pop out in the proof is going to look like I'm employing induction in a recursive manner. I assure you this is going to be kind of neat. So, like I said, it's pretty neat. And you can see quite quickly how you can take this and kind of build a regular expression into a finite automata, or finite automaton in singular. So there's going to be kind of, so I need to suppose language L is equal to L of R for some regular expression R. We build, so we're going to build an epsilon NFA. Build epsilon NFA E where L is equal to L of E. So that's going to be kind of what we're going to do, is we're going to build one of these epsilon NFAs, but this epsilon NFA is going to have a very special property, and we're going to use this to develop our induction proof. So this property is going to be very helpful for us. So I'm going to wear this, and psych, it's not a period now, it is a colon. And now I'm going to list you two properties. One, E has one final state, one final or accepting state. There are no arcs. Arcs, if you're not sure what arc means, remember, just think transition. Arcs leaving this state. So no directed edges that are going to come out of the final state when we're done. Now I must stress that this is in the case for which we're building the epsilon NFA at one given step of this process. So we're going to temporarily have a final state in quotation marks. And as we build it, the final state might shuffle around or become something new. So the second property is that there are no arcs or transitions toward the start state. So when I say that, I mean that within your epsilon NFA, there's not going to be an arrow, a transition, that's going to go from one state to the start state again. And remember, like I said, we're going to be building up an epsilon NFA for an arbitrary regular expression inductively. So this will be employed recursively. Like I said, induction, recursion, they're kind of like two sides of the same thing. Recursion is going to be very helpful for the way we look at this. So we use the recursive definition of a regular expression. To perform induction on R, the regular expression, structurally. So you're going to see I'm going to actually build an actual structure, which if you've never seen one of these kind of induction proofs before, I assure you they're kind of a treat. Structurally, ensuring E satisfies 1 and 2. So that's going to be kind of our goal here, is to just keep building up epsilon NFAs. And we want to ensure that when we're done, 1 and 2 are going to be satisfied for one given step of this process. So now I need to do the basis, and then I'm going to do the induction. Depending on how much time we have, we'll do an example. If not, we'll do it next time. Now, this proof is also fun because I get to draw you some pictures. But keep in mind, you can describe these more formally, obviously, because they're just transition diagrams. But remember, I want you just to remember that these are going to be like, the best way I could describe it is like we're building Lego bricks, but so we're making Lego bricks for our base step. And then as we build more complicated epsilon NFAs, I'm going to build more structures out of these Lego bricks. So what I originally told you was a final state will no longer be a final state. It'll become whatever the final state of the larger structure becomes. So I like to think of it like we're taking a smaller piece, we're building up using them. And it'll be very much how you actually employ this process. So for the basis, let's see here. There are 3 parts. To the basis. 3 parts to the basis of a regular expression. So remember, there are 3 cases. For like anything that wasn't just already a regular expression, right? Because I can recursively just go down if I've given a capital symbol for an expression in mind. So I have the 3 parts. We build E as follows. So I'm going to draw pictures as opposed to explaining to you in words. I have the full explanations in the notes. So I'm just going to explain how each one works and why it works. So the first case is when I have an epsilon. So when I have an epsilon, I'm going to design an epsilon NFA that's going to look like this. So I'm going to have this be my start state. And then I'm going to have a final state right here. And I'm going to allow this epsilon NFA to transition on epsilon to get to this final state. So the way I know that this will recognize the same language as the expression epsilon, which remember, this of course is the set that contains the empty string, is I have this epsilon move. And there's just a single path from the start state to the final state on epsilon. I think we're all good with this one. This is kind of cute, right? So let me just get rid of that. So next we have the expression empty. So the great part about this one is it's almost going to feel like I'm cheating, but it's not. Is that I can have a start state like this. I'm going to put a final state right here. But I'm not going to put any transition to it. And now I must stress, remember, we're talking about an epsilon NFA. This is perfectly fine to do because I'm allowed to have it where I don't have a transition from one symbol to another one, right? I'm allowed to have these in an epsilon NFA just because it's an NFA. So there's a third case. This is, of course, when I have a symbol A. So I have the expression that represents the symbol A. In this case, you might guess what it might look like is that I'm just going to have a final state, a start state, and I'm going to allow it to transition on the symbol A. So now notice that this is indeed going to recognize the language consisting of the single string A. It's because from the start state, I read an A, I get to the final state, right? So in all 3 of these cases, these epsilon NFAs, so if I just apply the appropriate case, I get an epsilon NFA. Are we all good with the base step? So that's really it. So I do have explanations for what I just described verbally in the notes. Now the induction. Now remember, we also had for the induction part all of our regular operators, right? So I'm going to have to take each one of those cases separately. So I'm going to assume the statement of the theorem. Assume the statement of the theorem is true for the immediate sub-expressions of the regular expression. I'll explain what I mean by that in a moment. i.e., the languages of these immediate sub-expressions are also are also languages we use to build the epsilon NFA with properties 1 and 2. So I'm going to call these two immediate sub-expressions. I'm going to call these R and S, not to be confused with the overall expression R, but it can be that one if we're talking about only one of these two. So if I have just like, if R was given to me and it's just straight up like one of these three, you know, that's R. I'm just using R to make it more convenient for myself when I define the star operator case. So when you see me say immediate sub-expression, I want you to think recursively. So I look at the overall expression. You know how I did it when I was doing it earlier at the beginning of this course? Not the course, the lecture. Sorry, I'm getting really excited about showing you some fun pictures. When I had, say, union, where I had one term and then I had another term, and I did the union over these two. Just like in my example when I was reading the decimals, I had E, F, and G, right? So I had F and G, and I did the union. Though F and G would be what I would call my immediate sub-expressions if I was evaluating inside of those parentheses. However, in the general case, what you might have is you may look at the concatenation and look at E, and then you would have everything else. So I'd recursively apply F and G afterwards. So you can either build it top down or you could build it bottom up. Preferably it's bottom up. So I would do the union and then I would take the concatenation of that result. Like I said, think of it like building things with Lego. That's sort of how I like to think of it. So I'm going to knock out these cases. I assure you it's not going to take me long to draw the pictures. But next time we'll do an example using it. So I'm just going to explain the justifications in each of the cases verbally. But in the notes, I have full explanations. So if you find yourself like not satisfied with my explanation, just take a look in the notes, okay? So the first case is when I have union, R union S, or R plus S. So in this, you're going to think about it like this. So I'm going to take my two epsilon NFAs, because remember the whole idea of the induction is that I can have, for R and S, I do have epsilon NFAs. So what I'm going to do is I'm going to build a bigger epsilon NFA using them. So here's my epsilon NFA for R. It's going to have a start state and a final state. I'm not going to double circle because I'm going to use these states respectively to build the larger epsilon NFA. Like I said, final state in quotation marks, initial state with no arcs going into it, quotation marks. So I'm going to have R and S. So this is my epsilon NFA for R, epsilon NFA for S. I'm going to create a new start state over here. I'm going to put epsilon transitions from this new start state to each of the original start states of those epsilon NFA. And then I'm going to introduce a final state to be over here, where I'm going to take the final states of R and S, and I'm going to put epsilon moves on them, or epsilon transitions. So when you read this and you ask, Dan, well, how do I know that this is correct? Well, look at it. Look, so I can take an epsilon transition to accept and get over here. I have to take a path that's within this brick right here for R. If I want to accept for the language S, I have to go and find a path of transitions to get me to here, and I can take the epsilon move to get here. Hence, I get this one or this one. So that's the example for union. Concatenation, if I give you RS like this, this one is much easier for me to explain to you. So watch this, watch this. It's gonna feel like I'm cheating, watch this. So I have the start state, end state, start state, end state of R and S. So I have a start state. My start state is going to be the start state of R. Then I'm going to put an epsilon move from the final state of R to the start state of S. And then I'm going to make S's final state the true final state for this case. Let me just make that double circle a little bit better. There we go. So notice that to get me to accept a string that's the concatenation of a string from this and this, for the languages respectively that are recognized by R and S, notice that I have to take a path from this start state to that final state, because there's only one final state, right? And there's nothing else going on, right? I have to take some path from here to here. That I know is a string that will be recognized by this epsilon NFA. Then I take the epsilon move. I have to go through this one. Same idea. Like I said, it's really kind of elegant, but it relies on us having these structures of the 1 and 2. So here's, now for our star, so the star operator, watch this. This is kind of nifty. So I'm going to have, so now you might be compelled to put the start state here, but I'm not going to do that. Instead, I'm going to put a new start state in place. And this is R. And then I'm going to make a final state out over here. I'm going to make an epsilon move to take me from the final state of the original epsilon NFA out over here. I'm going to have an epsilon move right here to get me to the start state here. Now watch this, watch this. So you agree with me that R star should contain epsilon, right? As a string that gets accepted by this new epsilon NFA. So what I'm going to do is I'm going to create a path that consists of an epsilon move that takes me right from the start state to this new final state. And now, because of property, I believe it's property 2 or 1 or 2, either way, I can guarantee you that the other alternative that could happen is I have to go through R to get to this final state, right? Now, when I reach this final state of the original epsilon NFA, I can either take the epsilon move to go here, or what I'm going to do is I'm going to take and create and add an arc from the final state of the original epsilon NFA to the start state. I'm going to put an epsilon move there. And now watch this, watch this. So if you take the epsilon, you can go here and you can guarantee epsilon's going to get accepted. If not, you can transition and you get all the way to the final state here. You can either accept here or you can go all the way around like you're taking the ride all over again. So I could go once, twice, 3 times, 4 times, 5 times, as many times as I like. But what's that? That's the star operator, right? So I can take the language of R as many times as I like. So I get one or the other. That's the language of R star. So is that clear, everybody? So those are our 3 main cases. And I want to just point out that all 3 cases satisfy 1 and 2. So notice that the resulting epsilon NFA in each one of these cases, it still maintains the same property. So all I'm doing is I'm using R and S as building blocks to build even larger epsilon NFAs. So I got 1 and 2 like this, thus completing the induction. And that's the end of the proof, believe it or not. That's it. So that being said, I'm going to stop right here. I apologize for going over a couple more minutes. But next time when we come back, we'll do some more stuff with this construction. I'll do an example with you. And then we'll get to the other part of Kleene's theorem. So that being said, I want to say thank you very much and have a beautiful day. So I'll stick around after to answer any questions.